Okay, so we'll continue with electrostatics. And from last time, we saw that we used two postulates. And the first postulate was that the divergence of the electric field, it was equal to rho divided by epsilon 0. And the second postulate, it was the curl of E. This was equal to 0. So we said that we can acquire all the necessary information for any vector field once we know the divergence and the curl. Now we know these. They are fundamentally true. We have never proved them differently using an experiment. And using the divergence theorem, we learned that we can, from this one, we can derive the following expression. EPS, and this would be a closed integral. This would be equal to the enclosed charge, Q enclosed, divided by epsilon 0. So this is the Gauss law for the electric field. And then we have also another expression, which was that EDN, this was equal to 0. And the first one, it was Gauss law. And the second one, this is the Kirchhoff law. Okay, and then, so this is how we started. We know how to derive these because we know the vector calculus. And then, initially, we can start with the aspect that the electric field, it is, we can always calculate the electric field from point charges. Okay, so this is the first thing that we can consider, and also we can calculate the electric field from a charge distribution. Okay, from a charge distribution. And when we talk about the electric field from point charges, in principle, we would have that the electric field would be the summary of several individual point charges like this, where I goes from 1 to n, and this addition is going to include expressions that look like this: I from 1 to n of k qi over ri cubed r. Okay. Now this expression, we know that. So first of all, just this is only as a reminder. The potential from a point charge, we write it like this. The potential V, it is kq over r, and the electric field, that is a vector, this is equal to kq over r squared ar. Okay. Or similarly, we know that ar, let me write it here, the unit vector, it is r divided by the magnitude of r. So in this case, we can also write this one as kq r cubed r. Okay. So we can simply, or just as a reminder, this is kq over r squared r. So they are all equivalent, only to also remember that this term is equal to this term. Okay. Now, whenever the charge distribution, it has some nice property or some symmetry, we can calculate the created electric fields using the Gauss law because it helps a lot. Okay. And now let's think for a moment, and then actually we can also think on. So this is the potential is measured in volts. This is the electric field, and then we have also the energy of a system. Let's write this one, the energy of a system, which can be described as K Q1, Q2 over R, okay? And we can also remind ourselves that the force between any two charges is equal to K Q1 Q2 over R squared. And the energy of the system is, in fact, this is the expression which is given for a specific case. And this one, it can be, this energy of the system, it is equivalent to reporting or it's equal to the work done to create a system. So just for a moment, let's imagine for a moment that we have the universe. It is empty, okay? The universe, it is empty, and we bring a charge into the universe, right at the center of the universe. We have a charge plus Q. How much work do we need to do to bring this charge at the center of the universe? The work done to bring this charge, it is going to be equal to 0, and here we are considering the work done in terms of using the electrostatic forces. If this charge has a mass, just like a mass, then the work done would be the following. It is going to be equal to the force times the distance, right? This is the expression for work. And the force is equal to mass times acceleration, okay, dot dr. That's good. So it has a mass, but we are considering that the work, the electrostatic energy work, will be equal to 0 if we bring this charge right in the center of the universe, okay? But now, this is M, this is the mass, okay? So let's leave this aside. Probably this is different from 0, but the work, because of the charge Q, this will be equal to the force times dr, and since we do not have a second charge, the force is 0, so this will be something 0 dr, and this is equal to 0. Because in order for the electrostatic force to exist, we need two objects, we need two charges. Now, the next thing that we can consider, let's consider this one Q1. Let's remove the plus sign, this is Q1. Now, what we want to do is that we have a new charge Q2 that we want to bring it closer to charge Q1, okay? And to bring it closer, we have to do work, right? And this work, it is going to be equal to, this is equal to force dot dr. Now, what this work is, this will be equal to K Q1 Q2 over R squared dr. But let's imagine for a moment that this force or this charge, we are bringing this one from infinity, okay, from very far away. So this is infinity down to radius r. So if we integrate these two together, what we get? We get K Q1 Q2 integral of dr over r squared. And dr over r squared, what is the integral of r to the power minus 2? The integral of this one, so when we integrate Rn, this will be equal to Rn plus 1 divided by n plus 1. Now n is equal to minus 2, so when n is equal to minus 2, the integral of r to the power minus 2 it is going to be minus 2 plus 1. This will be r to the power minus 1 divided by minus 1, so this is minus 1 over r. That's good. So then this is K Q1 Q2 minus 1 over r, integrating from infinity to, let's say, this one capital R. Now what we can do is that we can remove the minus sign, so we can write this one K Q1 Q2 1 over r, but we integrate, we change, so we remove this minus sign, and we change the limits of the integral, and this is what we obtain, and this will be K Q1 Q2 0, because 1 over r at infinity, this is 0, minus 1 over r. In this case, the work done in the system, it's equal to, work is equal to K Q1, Q2 with a minus sign, 1 over R. So this is the work done in the system, and this is also equal to the energy of the system, because the energy it's equal to they are equal to each other. Now, this is, and of course, it might be imperative for all of us that we're looking at this expression that the work or the energy of the system, it greatly depends on the charges that are involved, whether there is a positive, whether they both are positive or whether they are both negative, or one is positive or and the other being negative. Now, so this is how we can start to think about the electrostatics. And I believe last time we just did a couple of examples using the Gauss law. Okay. And let's consider a case where we have this uniform. Or let's consider so let's assume we have a charge which is distributed over a certain volume, and the charge density rho is equal to alpha 0. Okay, and then this means that the over volume of a sphere. Okay, and the question is find. So the question is this, which means that find the electric field as a function of radius, as a function of distance. Now, here we have our coordinate system, and this is our sphere, okay? And the first thing I may want to ask you is the following. What is the unit of alpha 0? Any idea? What is the unit of alpha 0? Andri? We could have a couple of Andris here. Yes, Andri Limana, yes, it's you. Or Coulomb per meter cube. Actually, somebody else answered. I think the Teddy. Okay, Teddy, let's see. This says that the unit is Coulomb per meter cube. Okay, this is the unit of alpha 0. Then, what we can do here is that we can use Gauss law. Okay, and if we want to use Gauss law, first of all, we can look at the symmetry. Does the problem have any symmetry? Yes, it has spherical symmetry, which means that we can select symmetry. We can select the Gaussian surface, which is like a sphere. So for a moment, let's assume that we are at a distance r. So let's assume initially that R is smaller than R0. So this is the outer radius, and we want to apply this rule, which states that E ds, this is equal to the charge which is enclosed over epsilon 0. Okay, so this is it. And then the terminology that we're going to use is the following. We're going to write the following. At a radius equal to R, select thickness delta R. Okay, so this means that at any radius R like this, we have to select an infinitesimal small thickness dr. In other words, we can say that në rrezën R, zgjedhim një trashësi pambarimisht të vogël delta R. Pse na duhet kjo? Sepse do të përcaktojmë një vëllim pambarimisht të vogël, so we're going to select an infinitesimally small unit volume element over which we are going to integrate. So we need to integrate because we need to determine what is the charge as a function of R. Okay? So in this case, we can say that the charge Q enclosed, this is equal to the integral from 0 to R of rho d volume. Okay, and by the way, what is the volume of this element here? So imagine for a moment, this is equivalent to asking the following question: what is the volume of the skin of an orange? Imaginoni lëkurën e portokallit, edhe po e dim rrezën e portokallit, po duhet të dim sa është vëllimi I lëkurës, që do të thotë po ta fusim në gotë me ujë, që është ngushtot me ujë, sa ujë derdhe. So what is the volume here? Who can answer this? So what is this infinitesimally small volume?
Should be the surface of the times the thickness dr.
Exactly, that's it. So what is the surface area?
4 pi r square.
Yes, times
dr.
Times dr. That is true. That is correct. Because the 4 pi r square, what is the unit of 4 pi r square? It's meter square, right?
Yes.
What is the unit of dr?
Meters.
That's good, so we get meter volume. That's good, that's correct. Now, what is the other way that we can do this? How can we find this expression using model technique? What we can do is that we can do the following. The infinitesimally small d volume, it is equal to the volume when the radius is r plus delta r minus the volume as a function of r alone. Okay? So you can try to see what you get from this expression, and this is going to be equal to 4/3 pi r cubed, okay, minus 4/3 pi r cubed. So check how much does this converge to this, okay? Consider this one and see what you obtain. Good, let's come back. So here, rho, it was equal, let's say this is equal to rho, it is equal to alpha 0. Okay, that's what was it. This was alpha 0 times 4 pi r squared dr. And we need to integrate this one from 0 to r. In this case, this is 4 pi alpha 0. What is the integral of r squared dr? R cubed over 3, and this will be equal to 4 over 3 pi r cubed alpha 0. This is the enclosed charge. This is Q enclosed. And then Yes, and then let's continue with this expression. We have here, let's write this here. This is E times 4 pi r squared. Let's not forget, we are still in this region, right? When r is smaller than r0. This will be equal to this q enclosed, which is 4 over 3 pi alpha 0 r to the power 3. Anything else? No, this is all divided by epsilon 0. 1 over epsilon 0. Now, in this expression, we can cancel out 4 pi's on both sides of the equation. Then, we take out this r squared, this is gone, and then we find that the electric field, it is equal to r, alpha r, alpha 0 r divided by 3 epsilon 0. Here we are. Okay. So this is the electric field. But now let's check if the units are okay. Okay. So let's see if the units are fine. And we can often use as a reference E, electric field. It is also written as 1 over 4 pi epsilon 0 q over r squared, right? So this is the electric field as we have learned it if we had a point charge. So in this case, we have the unit of 1 over epsilon 0, that's correct. This is coulomb, this is per meter squared. Now, so this is equal to the unit of 1 over epsilon 0 times coulomb times 1 over meter squared. This is what we learned in physics 2, which we know it already. Now let's come with this expression. Do the units match? This is 1 over epsilon 0 squared. Alpha 0, what was the unit of alpha 0? Coulomb per meter cube times meter, which is the unit of r. It looks like the units are correct. So we are good. Then, so this was one problem. Or let's say one way to put the problem. Let's think for a moment another charge density, but now let the charge density be equal to, so this is example 2, let the charge density rho equal to alpha 0 r, okay? And this is the density over the volume. If this is alpha 0 r, what is the unit of alpha 0? Any idea? So what is the unit of alpha 0? Here we found it was coulomb per meter cube. Okay, sorry, I got an answer here from Artiola and Brandon. You might correct your values, or let me think. Maybe Brandon is let's see. So this should be coulombs per meter cubed. So you can compare the answer that I received from few of you. Let me check again. So we have the answer from Andrea, Artiola, Brandon, and Clavy. Okay, so let's see. This could be coulomb per meter to the power 4 times meter. Okay, and this means that we have coulomb per meter cubed. So this looks correct. So alpha 0, it is best. So in the case of Andrea, it's a good answer, but we could choose as coulomb divided by meter to the power 4. We could select the answer of Brandon and Clavy better. Okay. So with this, so let's keep it for a moment over there, and let's now try to identify what is the electric field for R larger than R0. So let's not forget this, we're not done yet. Let's jump back to this problem again. And in this case, we can say that the electric field, so we're going to write an expression similar to this. Electric field times 4 pi r squared, this is equal to, and now this Gaussian surface, it's here now. So this is the Gaussian surface. The Gaussian surface is going to be 4 pi E times 4 pi r squared. So this is r. This is equal to Q enclosed. What is Q enclosed in this case? Q enclosed, here we have it. Q enclosed, let me write this correctly. This is alpha 0. This is Q enclosed as a function of r. Okay. Now, this is Q enclosed as a function of r. But what is Q enclosed as a function of r0? This is equal to 4 over 3 pi r0 cubed, now this is a constant, times alpha 0. Okay? And then, if we are out of the charged object, that means that if we get further and further, the charge enclosed is not changing. Okay? So in this case, we have to be careful. Give me a second. So this will be equal to 4 pi epsilon 0, so we are in this one. This is equal to 4 over 3 pi r0 cubed alpha 0, 1 over epsilon 0. Okay, then we observe that we can cancel the 4 pi's, and all these terms, they are all constants. So then the electric field, then it will be equal to, let's see what is that. Alpha 0 r0 cubed divided by 3 epsilon 0 times 1 over r squared. So what we observe here is that in one region, we observe that the electric field, where is it? It is proportional to R. Okay, maybe it is better if we write this one in this form. So these are constants times R, and here we have some constants times 1 over R squared. So if we are to plot the graph as a function of the radius, so let this one be R0. Now, a good homework for you would be to try to visualize how will the electric field change as a function of radius. And it looks like up to some specific value, the electric field, it is increasing linearly with the radius, which means that it is going to look like an expression like this. Y is equal to 3x. Okay? So this is how linear expression change, and then this electric field, it can go like this. Okay? And then, after some point, it looks like immediately the electric field, after it leaves the object which is charged, this is going to drop like this. So this behavior, it is proportional to R, and this behavior, it is proportional to 1 over R squared. So this is how this is changing. Now we have solved this problem completely. Sorry, this continues again. They never converge, of course, but this is how this will be dropping. Now again, let's see what will be the enclosed charge as a function of R. So let's write this one. Enclosed charge as a function of R, but now we are dealing with a different charge density. So again, the enclosed charge, it will be described as rho delta volume, and this is equal to alpha 0 R. This alpha 0 is a constant, we can take it out, but let's be a little more. Alpha 0 R times 4 pi r squared dr. So we need to integrate here. I'm not sure how much of the monitor you can see. Let me pick up for a moment. So this is equal to 4 pi alpha 0 r cubed dr. And this one is equal to the integral, it will be from 0 to r 4 pi alpha 0 r to the power 4 divided by 4. Okay. So we found the Q enclosed, and in the case when r is smaller than r0, the Gauss law, it reads the following: E times 4 pi r squared. So an expression which is like this. This will be equal to the Q enclosed. So this is equal to the Q enclosed is this 4. We cancel out to get here pi alpha 0 r to the power 4 divided by epsilon 0. So in this case, you can follow what we're trying to obtain. So we can cancel this out, and finally we can say that the electric field, it is equal to, let's get the constants in one place. This is alpha 0 divided by 4 epsilon 0 times r squared. Okay, so this is like times r squared. This means that and actually we may have to compare the expressions alpha 0 divided by 4 epsilon 0 r squared. So the same. So this means that at the same r, this is going to increase a little faster. Okay. Now this is in internet. And we observed that if the charge distribution was just a constant value, the electric field inside the object, it will change linearly. If it was alpha 0 times r, then the electric field, it will not increase as a function of r, but it's going to increase as a function of r squared. Then, let's see again, what is next that we need to do? We need to determine what is the electric field whenever the r, it is larger than r0, okay? And for this, we need to write a similar expression, which is E times 4 pi r squared. But now, let's also remind for a moment, when we do this, the Gaussian surface, it's right here. This is the Gaussian surface. When radius is smaller than r0. When r is smaller than r0, then the Gaussian surface, it is out here, which is much further than the outer radius of our object. So here we have 4 e times 4 pi r squared. This will be equal to the charge which is enclosed, and the charge that is enclosed, it is equal to pi alpha 0 r0 to the power 4 divided to the epsilon 0. Okay, and then let's see what we can improve here. So this is not improve, but cancel out. And here the electric field will be equal to alpha 0 r0 to the power 4. Now r0 is a constant divided by 4 epsilon 0 times 1 over r squared. So it looks like the electric field, when we have this charge density beyond r larger than r0, it is decreasing as 1 over r squared. Now a similar case will also happen here, where this will drop as fast as 1 over r squared. Okay. So this is another example. What you can do as a homework is to work this out. Example 3, where you can assume the charge density to be equal to alpha 0 times r squared. So depending on, because of different geometries, we could have different charge densities, and then you might, as you might assume, is that the dependency of the electric field as a function of the radius, it is going to be different. So let's not forget our initial question, it was this, find E as a function of R. And we observe that the E as a function of R, when R is smaller than R0, I cannot see it, it's here. So the major solutions that we are after are these. So it was this. Okay, when R it was smaller than R0, then we have this. Then this one here, and this one here. Now for this average charge density, you might expect different expressions as a function of R. Do you have any question for what we did so far? Not, we can have a short